how to analyze the correlation coefficient. When do you use the correlation coefficient? You have one continuous IV and one continuous DV. I use the IV-DV convention in this slide series to simplify our experimental thinking. Technically, we know correlation is not causation, and either variable could actually be the true independent variable in the world. However, at the end of the day, researchers must make a choice as to which variable to put first, and that is which variable to say is causing the other. Most researchers do have a causal theory when testing correlation. And when we make a scatter plot, we're choosing the independent variable because we place the independent variable on the x or horizontal axis. For a true correlation problem, the IV and DV are your choice unless I state otherwise. And you are free to choose whatever IV and DV you want to do for your own data. Just keep in mind that correlation is not causation, but it does help when you identify one variable as being the potential cause of the other, just to keep everything constant in your mind. As you get more experience with stats, you will forget this conversation. The goal of this test is simple: to test if two measures are correlated. And the correlation coefficient ranges from -1 to +1. A -1 correlation is as strong as a +1 correlation. Negative indicates as one variable goes up, the other goes down, like age and energy that you exert during sporting events. A positive correlation indicates as one variable goes up, the other goes up as well, as age and wisdom has proven by my case. Entering your data in Jamovi is simple. You should have a participant column that's just an ID type variable. You should have an IV column that's continuous and a DV column that is also continuous. Let's see what buttons to press, and make sure you enter variables in the same order that I do. Let's see that again. So our first question is, what is the pattern? Essentially, is this a positive or negative correlation? Now at the bottom, we can see a scatter plot. And this is one of the worst graphs that Jamovi produces. The independent variable and dependent variable are also labeled on these charts. And the independent variable is technically a label for the horizontal axis, and the DV, where it is technically a label for the vertical axis. It is very confusing, I do agree, but you have to trust me here that this is what's going on. But yes, I agree it is confusing. But ultimately, is this a positive or negative correlation? Well, we can see as variables on the independent variable go up, increase in value, the variables on the dependent variable go down. The dependent variable is the vertical axis. The independent variable is the horizontal axis. So we see we have a negative correlation. Is this a significant correlation? Our p-value. Is it less than 0.05? Yes, it is. Significant. If it's greater than 0.05, not significant, inconclusive. The 95% confidence interval suggests that our true population correlation ranges from negative 0.64 to negative 1.0. So before we even look at our effect size values with small, medium, and large, we know that the population correlation is negative. Now, a small correlation is 0.1, a medium correlation is 0.3, and a large correlation is 0.5. Correlation is one of the most sensible and makes the most sense statistics that we use because the actual statistic is an effect size measure. It's one of my favorites because it's very simple. Now, earlier I taught you all about R squared, percentage relationship. So when you square your R, you get the percentage relationship between the IV and the DV. And like a 0.1 is small, so 0.1 squared is 0.01 times 100 is 1%. A 1% relationship is small. 0.3 times 0.3 is 0.09 times 100, 9% relationship is medium. 0.5 times 0.5 is 0.25 times 100 is 25% large. So I do like the R squared values, but you can interpret and should interpret your correlation coefficients. We can see right here that we're either the true population value somewhere between 100% related and about 80, a little bit greater than 6 times 6, 0.6 times 0.6, it's like 36, a little bit more than 36%. Either way, all of those correlations are large. We know the true population correlation is negative large to negative large. Again, I make up my data. Your data are very unlikely to be this massive. The correlation coefficient is actually something that we can understand. So I'm going to teach you a little math. First, you have to understand the concept of standardizing a score. Now, if you look at the column of data for the independent variable, to standardize that column of data, we would find the mean of that column and the standard deviation of that column. Then for every score, we subtract the mean and divide by the standard deviation using the order of operations I show on the slide. If we do that for both variables, and plot those new variables in a scatter plot, the correlation coefficient is the slope of the standardized scores. So all this means is a 1 standard deviation increase in the IV is associated with a blank standard deviation increase or decrease in the dependent variable. So in this case, a 1 standard deviation increase in the independent variable is associated with a negative 0.97 standard deviation decrease in the dependent variable. And that is all a correlation coefficient is.